Yes, thank you. So my name is Owen. I'm a PhD student at K11. And I mainly now want to talk about how we are using detailed atmosphere and wind models to derive mass loss rates for more than just O stars, which is still on the schedule, but also for B-type stars and for other massive stars, and see how it influences their evolution. So I want to iterate again on how mass loss can be important for massive stars. It's a key uncertainty in many evolutionary stages. And it's important in that it provides a chemical and mechanical feedback to its interstellar medium. But also, of course, it influences the life and the death of the star itself, with one concrete example that it affects the mass of the black hole after the star dies. With here as example, we show a figure from Belsinski et al., where we have here the resulting black hole mass after the evolution of a star with a certain initial mass. And if we assume the standard wind prescription, we get these masses of black holes, while if we reduce the mass loss, this could potentially create much higher black holes. So this is one concrete example of how mass loss can affect it. So we want to be able to describe such mass loss, and this mass loss arises from some radiation-driven outflow. And for the hot stars that I will be looking at, it's line-driven winds. And these cause very extended atmospheres and winds. So if we want to describe them in detail, we need non-LTE radiative transfer to model this interaction between the radiation and the matter. So for this, we turn to the one-dimensional code fast wind, which we'll use to construct our wind models. So as important for these models is that we want to have them dynamically consistent, which means that this equation of motion here in the steady state spherically symmetric case needs to be satisfied. So what we get from the radiative transfer that inputs here is mainly this radiative acceleration. So in a small schematic on how these wind models are constructed, we need to start from some initial guess of the wind structure and the mass loss rates and solve the radiative transfer here. From here, we get the radiative acceleration that feeds back into the momentum equation. And this we need to solve iteratively to get a converged solution. And for this converged wind model, we then get an associated mass loss rate and velocity structure, and also, if we want, a synthetic spectrum. So this type of setup we can use to study the behavior of the mass loss rate over the Hertzsprung-Russell diagram. So we did this for a set of O stars already, and here I show a setup for a larger part of the HR diagram, where we have wind models covering the effective temperature, luminosity, and also this fake third dimension of the mass here, also for different metallicities. So from this setup, we then get these wind models and thus the mass loss rates for all of these points. And we can then study its behavior with for these fundamental stellar parameters. And then such prescription, such a recipe, depending on these parameters, we then can compare to, for example, observations. Here I show a set of observations of O stars, which are adjusted for the clumping in the wind, because this clumping can, of course, affect for certain diagnostics the mass loss rate you derive from them. So for more detail on these empirical mass loss rates, you can also look at the talks by Callum and by Sarah. But in general, you can see, well, there is of course a large scatter, but there seems to be quite a good agreement with the general trend and the general order of magnitude for these observations. What we can do as well is compare them to existing theoretical predictions, where I also again compare it to the rates by Vink et al., which are commonly used in evolution models. I show here a sequence of mass loss rates just for a constant luminosity and mass. And what we can, for example, see is that for the O stars, we have a certain reduction by an order of a factor 2 or 3. But maybe more striking is that we have a larger discrepancies at colder temperatures. And this is below the so-called bistability jump. And this is because iron 4 recombines to iron 3, which in the Vink models adds a sort an increase of the mass loss rate by approximately an order of magnitude. However, we do not find such an increase from our models. That's why we have a larger discrepancy here. And to go a bit further into detail on why we do not find it, we have computed additional models which are not self-consistent, but instead we try to drive a higher mass loss rate using then also not a consistent velocity structure, but a beta-type velocity law. And then here we can see the result of this, where I plot just this gamma factor, which is Girard over your gravitational acceleration, compared to the other terms in the equation of motion. So in the case of a consistent solution, these lines should fall together. Another way of looking at it is that we compare the gamma that we get from the radiative transfer to the gamma that the model needs to drive this kind of wind. And what we see from here is that in our case, for this type of model, we lack the force that we need to drive an outflow through the sonic point of such a high mass loss rate. So in this case, our models, if we would then continue to solve them towards a consistent solution, it would favor the lower mass loss rates instead of these. So if we now look at how this impacts the stellar evolution, we have, I show here the evolutionary track of a 60 solar mass stars using the different mass loss prescriptions. And I want to focus on two results here in this plot. One of them is that if we use our reduced mass loss rates in this solid line, we see that the star ends up on the cooler side of the HR diagram, and thus it does not have enough mass loss to strip its hydrogen-rich envelope to form what we call a Wilfred star. So we seem to have trouble creating Wilfred stars through a single star channel. Of course, these stars could also be stripped through binary interaction, but for a more empirical approach to this topic, I advise to look at Tomer's talk. Another thing we can see from such evolution calculations is that the final mass of the star before it dies is higher because less mass is lost from its envelope. And this could directly relate to the mass of the black hole that it leaves behind. So here I show a small figure of a study that I did together with a master's student, where I again show the final mass of the star or the resulting black hole compared to the initial mass of the model. So in this case, we look at the helium core mass of the star, which we then assume determines as which type of supernova it would explode. So, and if this mass stays below this line of which determines if it would explode as a disruptive type of parent stability supernova, it can instead directly collapse and adding its core mass and its envelope mass to form a high mass black hole. So what we saw in the Belczynski models, where there was an ad hoc reduction of the mass loss rate, here with our reduction, we find we could also reproduce potentially higher mass black holes. So in short, in summary, so we have computed detailed wind models to provide new mass loss predictions, which seem to be lower than the ones previously derived. And additionally, we do not find a bistability jump from our models. Additionally, when we look at them in the stellar revolution, we have trouble creating Wilfred stars, but we do seem to be able to create higher mass black holes. However, of course, we still need some mass loss across other parts of the HR diagram. We, for example, are missing the models at very high luminosity, which relate to the very massive stars. On the other hand, we could, there's also potential other ways of stripping the envelope to create Wilfred stars. I mentioned the binary channel, but of course, other things that are not yet implemented in evolution calculations are mass loss through eruptive type of event, or LBV mass loss. So this could potentially strip a single star to become a Wilfred star, even including R reduced mass loss rates. I thank you for your attention.